Okay, all right, folks, let's get going. So here's the definition. And we have if f is differentiable at A, if this is the case, then f will be continuous at A. So one of the things to understand is that in if then, see right here, so we're going to do some logic just a little bit. In other words, we can write this with an implication. Right? Do you guys know this thing? This is called implies. If you have a function, okay, so if then is called an implication. So it only goes in this direction. It doesn't go back towards that direction. That would be if and only if. This is if this is if this is true, then this is true. If and only if is like this, right? You put two of these guys. We don't have that situation. So in other words, what I'm saying is that, Zara, pay attention. Now you're in the video. That's the way to put you in there. Sophia? Yes, good. Okay, okay, so what was this thing here? Is that one way to formally say f is differentiable at A? Yes, because this is the derivative, right? If f is differentiable at A, f, we can calculate the derivative at A for that function. Okay. What was the okay, sorry. So there's something called something that we take the limit of. What is that? To get, okay, I'm gonna restart. Does anybody know if Emma is coming or she's gonna be late or she's coming? Okay, we'll just wait. Because I want people. Who? No. I want to shoot Zara. Sorry, Zara. Yeah, thank you. Very, very much. Oh, nice jacket. Nice backpack. And also make sure if the bottle comes down and falls out, it's not my fault. Okay, yeah. So also another thing. When are you graduating? This is your last semester? Or? Okay, so this spring. Okay, so here's one thing. If you aren't going directly to graduate school and you guys are graduating, one thing you can do is apply for admin positions at CU, CSU, Metro, DU, because you get healthcare, you get a job which is white collar, and then you can even start as a receptionist, and then you can move up. And then you'll make more money than I am. No, I'm just saying, otherwise there aren't a lot of jobs. So, and it's a good job because you can't get fired. We've had people, you couldn't fire them. There were alcoholic people who would show up drunk, and it was all fine. So some of the best jobs are right here, big campuses. I told one of my students to apply, and she didn't bother. Guess what? Her girlfriend is a chef. So what is she doing? She's going to be a waiter. Right? Because if your girlfriend, then you have the working class solutions and then the middle class solutions. So that's for you, warning. So make sure you look for middle class solutions in your life, Zara. Oh, I love those. Can I have one? Okay, the class begins now. The sermon is over. But there are these, thank you. Oh, God bless. Haribu. It's not even salty. Why is it not salty? Oh, no, so that is, there are people already in the department who get those. They won't let me have. Plus, do we have even any grading work in this class? I can put you as on, we can do a fake thing and then you can put it on your CV if you want that. Okay. And then we'll have the whole thing. And then if they call me, I'm like, of course he worked for me. All of that. And then if I write a letter of recommendation, I'll put that in there too. Okay. All right. Because I try to get that. It's the people who actually, there's that guy who does the computer science STEM thing in the English department, and he gets the TAs and all that shit. Okay, all right, so let's go back here. If f is differentiable at a, then f is, and I want questions and people to stop me so we can have a good class. If f is differentiable at a, then f is continuous at a. So another way to write this is if you have if and then what you have is called an implication, and it goes only from the right to the left. So f is differentiable at a means that at a, the function has a derivative. So this whole thing can be written like that. What's the other way to express this idea? If people remember, there was something called a quotient. What's the first? There's a phrase, quotient, and then there's another word before that. STEM people? Difference quotient. So we have difference quotient. Thank you. And then what do we do with the difference quotient? We take the difference quotient gives us what? The average rate of change, the average slope. And when we hit the difference quotient with a limit, we get the instantaneous slope, the rate of change at one point. Average rate of change means you have to use 2 points. And calculus allows us to figure out rate of change at a point. Okay, and it's all souped up mathematics. So what is so I'm gonna write out. So let's do that. What's the difference quotient here? For this, we're using the a and the h. So f of a plus h minus, anybody? Thank you. And then all divided by, this is the quotient, is another word for fraction. Difference quotient is a difference fraction. And h, because a plus h minus a, those two guys can get canceled. And then the limit, right now, this gives us what? The average rate of change. And we calculate that by having 2 points on the graph. And then what do we do to make this a derivative that gives us the rate of change at what point? We apply what to this quotient? STEM people? Very good. STEMers, may you live a long life and happy. So we have this. Then, this is Star Trek 101. Then f is continuous. And what's the formula for continuity? She has something going on. This child, this is not my child. She has a microphone and a speaker. All right, folks. Zara, you are failing this class. And you're going to be famous because I'm not going to delete this. No. Yeah, he's got an A. I fixed it. Okay. What's happening here? What's the definition of continuous at A? Anybody? Give. Yes. So we have the limit on one side and the value of the function at the other side at the point of interest, right? So value of the function at A better equal the limit of the function at that point. If that is the case, then the function is called continuous. So what's happening here? This is an implication. This thing implies that this will be true. A continuous function is not necessarily differentiable? Well, let's look at this one here. So let's say we have, if f is continuous, implies that f is differentiable. And let's do a quick example here. This is differentiable, badly spelled here. Okay, so the picture is f is continuous, so I'm going to draw a picture. Is this continuous? Can I, but is it differentiable? And the answer is no. A continuous function like this cannot be differentiated because I cannot stick a tangent line at all. Is it this one? Is it this one? Is it this one? So we can't do that. And so it just doesn't work, even though it's continuous. So in other words, this is the true definition of a differentiable function. This is the true definition or the condition for a function that's continuous. And what we're saying is if you have a differentiable function, that implies that at that point A, it will be continuous. But if you have a function that is continuous at A, that does not mean that it is differentiable at A, as this picture shows. Okay. All right. So let's keep going now. Oh, okay. As in this part or this part? That I'll leave there. Yeah, I'll leave that. Okay. So the whole thing is, why do we start here? Because what happens is we assume this, and then the second thing we assume about this function. So the way when we start here, we're saying that actually at the end, this is what we need to show. In order to show this is true, we have to do this. All right, and then what happens is there's that trick that happens that's confusing. All right, I'm just gonna jump in and then people stop me. Is this the shit? As in, don't jump in or jump in. All right, proof. So where did we start last time? With the consequent, the thing that we want to prove. This is the true definition of continuity. This is the true definition of differentiability, whatever that thing is. But the problem is, we assume this to be true, and we start here, and then we bring this guy in, and it all works out. So we started the consequent, the thing that we want to prove, and we write limit okay, so this is the proof here. Anybody help me out here? What's the next step? No, not the stem. Very good. So when is this thing true? When is x and c are equal to each other because their difference is equal to 0. So if you get something like that, in order to show that their equality, you have to show that their difference is 0. So we start here. F is a function that is, we've assumed it is differentiable, but we don't know if it's continuous or not. So we have to show it is continuous, and then we bring this in at the right moment, and then everything will work out. So we do what Sophia just said. And now we have that. So x equals 0. How do you show it if the difference is equal to 0? Now we got that. And this is where, and then in which direction are we? We want to start here and make it look like that. Is this already looking like that? Right, because now we have f of a plus h minus. So we got the numerator already. And we have the limit already, right? And we just have to divide it by h. Okay. And but what we want is this whole thing equaling something. So next step is but and I think that was missing, right? This, if you have a fraction in front of the limit sign, the limit applies to the whole fraction. Right now, the limit is only applying to this bit here. It's not applying to the whole difference. So that's the next step we have to do. So we go but, so what we do is we take the left hand. So we are now just working with the left hand side here. So, but in fact, we can apply the limit to both sides. And why? And the reason was we can apply this to this guy because it doesn't matter, it doesn't have an age. Okay, all right. Then at this stage, we're almost there. So we can do what? Next thing we're going to do is, I want to make sure. Yeah, I'm going to do it right here. Otherwise, it'll be okay. So now I'm going to, now I am in the position to make it look like this side. And as soon as I do that, okay, so we've got this. I rewrote this on this side, and I'm going to do what? Multiply and divide. So I've got this thing here. Then I'm like, I'm going to now multiply and divide it by h. So I go equal this whole thing, divided and multiplied. Just a step, right? Okay. Now what do we do? We don't, so now that this looks like a, because the thing is we started at the consequent, and then now what do we have in this? We have been able to incorporate something that we have assumed true into what we were manipulating. So we started with the consequent. We don't know if when we start this proof, we don't know if differentiable functions are also continuous. We have to show that. So we start with the definition of continuity, and then we stick in, then we manipulate it and make it look like that the definition of differentiability comes in. And then if this whole thing equals 0, then this function is also continuous. So for instance, I want to make potatoes and meat. And if I add potato in, okay, all I have is, let's see, I have meat and potatoes implies potatoes. No, that doesn't work. Let me just say this here again. This is assumed to be true. This is what we are showing. If this is assumed to be true and it gets stuck in here, and if this thing doesn't end up equal to 0, then a differentiable function is not continuous at A. All right, so let's do this again. So we start at the consequent, this part. I write it out right here. Then I say that this is true if the difference of these two guys is equals 0. Then I go, but I know that this thing, in fact, I can apply the limit. Right now, the limit is only applied to this, but we can also apply to that, and it doesn't matter because this term doesn't have h, so I put that. And at this stage, I multiply and divide h. What has entered the discussion of the consequent? The derivative has entered. Something that we have assumed true. Something that we have assumed true gets in. If this happens, what does that mean? If we calculate this thing, we apply the limit and do all the magic, and we get a 1. That means this didn't happen, which means we assume that we were dealing with a continuous function, but that continuous function, why is this function continuous? Because the difference of these two things is 0. So, and then we put something that was true about this, that we put in the definition of differential. We put in the definition of the derivative, and it messed it up, and we got a 1. If we get a 0, the difference, then what it means is that that a derivative, differentiable function is also continuous. Okay, so if you get a 1 here, then bringing in something that we have assumed into, so this is the assumed to be true, we bring that in. So we are saying, what are we saying here? We are hoping that the function f is continuous. We're hoping the function is continuous. We know it is. We have assumed it to be differentiable. We bring that into this thing, and it fucks it up and gives us a 1. If it gave it what we assume to be true goes into what we are hoping to be true and makes it false, or 3, or whatever. If we get 0, that means it is not only continuous but also differentiable. Two things. Does that make sense? Is it still no questions? Okay, all right, so let's keep going. So now it's just pure algebra. And here what we do is we the limit is applying to just a fraction, but not to h. So just like before, whoa. What is the first limit equal to? The derivative, right? This is just a definition of the derivative. So that's a number times, what's this equal to? If you apply the limit as h goes to 0 to h, you get, since this is a polynomial, you just do substitution. You guys remember that from calculus? And then we have 0. All right. If this guy was 1, we would end up with 1 here, or some number. And that would mean that, okay. All right. Ask me questions before we go to, I'm going to go over the poem and the next assignment. That's what we're doing. Okay. I'm just going to go over one more time. This is an implication. This is assumed to be true. So we use it. This is what we want to be. This is what we want to be true. This is our wish. And the functions are same. It's the same f function. that we're dealing with. That's the other key thing to remember. We're dealing with the same function that we assume to be differentiable, and that same f function we want to show that if it is differentiable, it better be continuous. The other way around is not true. A function can be continuous but not differentiable. Next, we start here because, yes. No, because I was just pretending that this thing was here and continuous was here. So let me try again. Function that's differentiable better be continuous, because this theorem is true. The opposite theorem, which would be on the antecedent, we would have, or the hypothesis would be, if f is continuous, then it better not be differentiable. It is not necessarily differentiable, and that is true. Majority of continuous functions are differentiable, but there are continuous functions like the one with the corners are not differentiable. Now, we want to show this to be true. How do you show this thing to be true? If it equals 0. And what do we have to make this thing show this to be true? We have this assumption that we can use. This is the fuel that goes into. All right, so we have, we start, this is what was in the consequent. Then we brought f of a to this side by doing the adding, subtracting on both sides. And then we want this to be on the left-hand side and this going down like that, so that we can show this equals 0. So we go, but this is the way to get out of this situation here. So that's one trick in the proof. And then we go, but we can actually apply the limit to both terms of the difference. And if and then we can actually multiply and divide by h and not changing what we have here. So this side, the right-hand side, is equal to the left-hand side. Next thing, we look at that and we go, oh, that looks like our assumption has come into our algebra here. If this is not true, if this was if this theorem was incorrect, a false theorem, then putting something, assuming this to be true would make, and by false it would mean that a differentiable function is never continuous, right? That would be the false thing. A differentiable function is never continuous. I put in this assumption that our f, that same f, which we are hoping is continuous, is also differentiable. So we put that in and it fucks it up and we don't get a 0. But because but it turns out that a differential function will be continuous, and by sticking this in, we still get a 0. 0 means that it is continuous, because 0 is this thing here. Okay, so for instance, I'm going to write this here. Limit of f. Oh, that's terrible. Let's try that again. This is the definition of continuity with the a and h thingy, right? So the limit of the function at a equals the value of the function at a. How do we show this to be true? If the difference of these, when are these two equal? Their difference equals 0, exactly. If this had come out to be something else, then what we have is a situation where the function is differentiable but not continuous. Let's say this was 1. We will end up with the value of the derivative, which is a number. Now what's happened is we wanted to show it was continuous. We've assumed that to be true, and we're hoping for a 0 here. Our f, we have assumed to be differentiable. When we put that fact into the mix, it fucks up the calculation and gives us a number, not a zero, telling us that this function is continuous, that a differentiable function is not also continuous. If you get this, if you get a zero, then it's saying that a differentiable function is also continuous and must be continuous. Good? Okay. All right. So on Wednesday, I'm going to start integration. And we're going to go through a few things in integration. And then I'm going to give you the assignments earlier on. And then I'm going to do some cool stuff, random stuff that we didn't do. Some sequences, and then metric spaces and all that stuff that I did with Ryan. We'll do a little bit of extra stuff. Okay. All right. Now I need the computer over there. So I'm not going to switch the camera because this is not for the gods of the YouTube.